Okay, so you've heard some laboratory talks and you've heard some clinical talks, and I'm going to do both since I work on both sides of the street. This is the clinical part of my talk. As some of you have probably seen before, we ran this trial. This was with patients with primary disease. Mostly we've talked today about recurrent disease or metastatic disease, but this trial was run in patients who had their initial tumor without any sign of spread at the time of diagnosis. And so we ran this trial for 5 years or so, where we took patients from around the country that had at least a 3-centimeter tumor. We said, well, there has to be good surgery, it has to be removed, and we have to prove that it's a GIST. And we randomized the patients to getting 1 year of placebo versus 1 year of imatinib. And this was because the standard of care at the time was actually to do nothing, because we never had a drug that was effective. So if you had a primary tumor in the 1990s, you got an operation, and that was it. You may not even have gotten a follow-up CAT scan. Things are quite different today, of course. So we ran this in a double-blind fashion, so the doctors and the patients didn't know who was getting what. We followed the patients. We had some 200, 250 centers across the country participating because it's an uncommon disease, and we eventually got to about just over 700 patients, which was about 30 or 40 short of our target goal. And the trial was stopped because the data, which was evaluated by an independent board of physicians and non-physicians, showed there to be such a large difference between the two arms that in all right, we had to stop the trial. And this is, you've seen some of these curves today, but they're probably not familiar to you at all. So I'll just mention briefly. So this axis is the number of patients who are alive that have no tumor. And of course, when they started the trial, 100% of the patients had no detectable disease because they just had an operation for their primary tumor. The blue line is patients who were treated with imatinib, and the dotted line is those who were treated with placebo. And so every time a patient develops a recurrence, the line drops by a little bit, okay? So we gave the patients 1 year of imatinib, and what you can see during that 1 year of time, basically nobody who was getting imatinib developed a recurrence. In fact, it turned out to be 2% of all the patients who were getting imatinib. In terms of the placebo group, well, you can see this line falls very quickly, meaning lots of patients were developing recurrence after having the operation on their original tumor. And this turns out to be about 18% at 1 year. And then what you can see is after the drug was stopped in the blue line, well, then the rate of change, the sort of slope of the curve, became much greater, meaning that a lot of the patients who had been suppressed initially to have a recurrence then developed a recurrence after the drug was withdrawn. In both cases, anytime anyone on the placebo arm developed a recurrence, they were then switched over to imatinib, and anyone who had stopped imatinib was restarted on imatinib. So this trial changed the standard of care in this disease, which is uncommon for a single trial to change things dramatically. And now we give many patients 1 year of Gleevec after surgery, and as you may have heard recently, another trial built upon our trial showed that 3 years is better than 1 year for at least a subset of the patients. And I'll show you how we approach that in a minute. So this was the FDA approval in around Christmas 2008, and then this is the European version of the FDA. They followed right after our country changed the standard. So we had all these patients on the trial, and then we started to say, well, you know, not everybody developed a recurrence, so how can we really identify the patients who need the drug the most? And this is a mathematical formula called a nomogram, and based on the characteristics of the original tumor, we made this mathematical formula with one of our statistical colleagues here, Mitat Gonen, and we had this formula that predicted the likelihood of recurrence for any one patient, which of course you can't be 100% accurate, every patient's different. But then we took our formula and we applied it to a bunch of patients in another country with GIST, and then people out on the West Coast with GIST, and it seemed pretty valid. So this formula is actually on the internet, and we use it all the time, and people from around the world use it all the time to try to estimate what's going to happen in any one person. Again, this is an estimate. Nobody knows what's going to happen in the case of one person, but we know what will happen in the case of hundreds of people with similar characteristics. So the trial, that original trial I showed you was called Z9001. This was our second clinical trial that we've run. And using a different stratification, not the nomogram stratification, we now know that about half of those 700 patients that participated in the trial, based upon what we know today, we would not give Gleevec after surgery because we can now identify them as being at very low risk. So at 2 years, 2% of patients in what we call the low-risk group actually had an event, meaning they had a recurrence. So half of the original 700 patients we wouldn't even treat today after surgery. We'd continue to monitor them, but we wouldn't treat them. And those at moderate or high risk, we would continue to treat them. Now, we can take that a bit further. That risk was just based on size of the tumor, activity, the mitotic rate that you hear us talk about, and location. But in addition now, we have some other data looking at the type of mutation, and we're preparing this to submit for publication. Basically, for patients with KIT exon 11, there's a big difference between the blue curve, those who get imatinib, and the red curve, those who got placebo from our study. So we think that exon 11 patients should be treated with imatinib after surgery. Those who don't have an identifiable mutation, well, you can see that these curves are virtually identical. And these patients we tend not to treat now, because it doesn't look like there's a benefit. And the KIT exon 9 mutations are somewhere in between. The blue line, it looks like they're suppressed during that 1 year of therapy, and then when we stop the drug, then the chance of recurrence is much higher. So we've shrunk the pie, so to speak, quite a bit. Out of the 100% of patients that entered the trial, it's probably now down to somewhere around only 40% of the patients would we consider for therapy at this point. We knew that this other trial that I mentioned, the 3-year trial versus 1 year of postoperative therapy, was likely to be a positive trial, meaning it would show a benefit. So we started a phase 2 study a couple of years ago, and this was clinical trial number 3 for us. And we already have 91 patients who are now getting 5 years of postoperative therapy, and these are patients at what we call significant risk, and I've defined it here. It's not crucial to know the details. So what this meant for us was that in many cases after surgery, the drug was more suppressive. We're not sure how many patients were curing, but we know it suppresses the development of recurrence. And so, in that respect, you could argue that imatinib is very effective, but it's not good enough. So we started looking in my laboratory at other ways that we could make imatinib or other tyrosine kinase inhibitors more effective. And you heard about the mouse model earlier. This is a GIST tumor in a mouse. This is created by the Besmer lab. This is the scientific citation. And basically, these tumors are very representative of what we see in human beings. They're not as aggressive as some of the human tumors, but we think they're very indicative in some cases of how a human tumor would respond. So let's look a little more at this model. So one of the first things that we did was we started looking at the immune cells within the tumor themselves. And what we found was that the nearby lymph node didn't really tell us anything. And we're looking at 2 types of T cells. T cells are immune cells that fight viral infections, bacterial infections, and cancer. And here we're just looking at the ratio of the number of CD8 T cells, which are sort of the good T cells, they destroy things, versus the regulatory T cells, the Treg, which kind of suppress the immune environment. And what we found in the lymph node was if we gave a week of imatinib, there was no difference in these cell numbers. But what we noticed was that there was a big difference in the tumor. In the mice that got imatinib for a week, there was an increase in this ratio, meaning there were more CD8 T cells and there were less T regulatory cells. And this was pretty striking, and nobody had ever looked really at the T cells before in these tumors. So this is a complicated slide, and I'm just going to make it simple by getting rid of some of the control groups. When we do an experiment, there's many times where we need all kinds of controls to prove what we're trying to conclude. So just to keep it simple, what we're showing here is the weight of the tumor. So we took a whole cohort of mice, 8, 10 per group, And we either gave them vehicle, which is like salt water, or placebo, if you want to look at it that way, or we gave them imatinib, or we gave them imatinib and we depleted these good T cells, the CD8 T cells. And what we noticed was the effects of imatinib were not nearly as good when the CD8 T cells weren't around, meaning the mouse was somewhat immunosuppressed. And these findings were a little striking because we normally thought of imatinib as working solely on just knocking out KIT and resulting in cell death of the tumor. So you've seen some of these arrays, and they make these really colorful pictures. But what we've done here is we've taken each column. There's actually 3 columns here under placebo and 3 columns under imatinib. And these are 3 different mice. And we're basically analyzing the expression of tens of thousands of genes to try to figure out what's different, what happened by giving imatinib. And one of the several things that popped out was this protein called IDO was lowered by giving imatinib. Now, IDO is complicated. I'm not going to go into it in very much detail, but basically, after months and months of work, what we found out was that the GIST tumor cells themselves were making this protein, and the protein is well known to sort of cause immunosuppression in the immediate environment of the tumor. And what it does is it sort of inhibits CD8 T cells but activates T regulatory cells. So this is bad, right? Because in this environment, the CD8 T cells that normally might want to kill the tumor can't do that. And what we found was that one of the side effects, so to speak, of imatinib is that it knocks down this protein being produced by the tumor cell. This IDO protein goes much, much lower and very quickly within a few hours. And what this allows is for the good CD8 T cells to sort of wake up and proliferate, whereas it inhibits the T regulatory cells. So this is a very simplified version of what we found, and but this was quite striking because nobody had made this connection before between imatinib and IDO. Well, that's all nice to have mice where you can create a big difference in them, but of course the most relevant question is what does this have in terms of significance for human beings? So pretty much every patient that we operate on here, we approach them, and it's voluntary, and we ask them if we can take their name off the tumor and investigate their tumor to try to learn more about it. And so this is a series of 45 specimens that were taken right from the operating room. It passes through pathology, and most specimens get discarded after the pathologist takes the piece that they need to look at. And so we took the remnants of these tumors and we started analyzing them. We took them straight to the laboratory and we looked at the number of CD8 T cells, these good T cells, and we looked at the T regulatory cells as well. And forget the blood. The blood doesn't tell us anything. It's all about what's happening right around the tumor. And so what we have here, each dot represents a different patient. And U means untreated, meaning they've never seen imatinib. Sensitive means they've been on imatinib and their tumor is not growing. It's either stabilized or it's still shrinking. Whereas resistant means they've had imatinib, and some of these patients have had sunitinib, and their tumor is actually actively growing. And what you can find is, just like we found in the mouse, essentially, when we give human beings imatinib, within their tumor they have more CD8 T cells, and at the same time they have less T regulatory cells. And we could also show that IDO correlated with this. Now, to simplify showing you each individual dot, we can summarize it statistically here, where again, the untreated patients, relatively low CD8 to T regulatory ratio. The sensitive patients, it goes much higher. And then resistance again, it flips back. So we found that T cells were important in the effects of imatinib, and the next obvious thing to do was to say, well, why don't we give a boost to the T cells and see if that makes things even better? And we performed the following experiment doing MRI examinations serially on these mice, so we can do pretty much any test that we do in humans in mice. And we did one of 3 treatments. We either gave the mice this compound called anti-CTLA-4 alone. This was just approved for the use of melanoma. It turns out it's effective in about 10 or 15% of patients with melanoma. This is a T cell activator. So we gave them that alone, and we saw that that results in a little tumor shrinkage, but then the tumors start growing again. We gave them imatinib, just 1 week of imatinib, and we found the tumors shrink, but then they start growing again. But if we gave both treatments, 1 week of imatinib only, a little different than how we might do it in human beings, but 1 week of imatinib plus anti-CTLA-4, we got some stabilization of tumor growth. So Rich is going to talk a little bit more about this, which turns out to be clinical trial number 4 that we've tried to be involved with. So we have lots of other stories going on in the lab. There's not enough time to tell you about them, but we have several other exciting things based on the immune system that we've been working on more recently. This is just a fraction of the different people that have helped. A lot of the T-cell work was done by Vinod, who's no longer in the lab, and then this is the current lab right now. This is the different funding agencies that we've had, and the GCRF, which has supported us for the last couple of years, was really one of the first sort of seed monies we got to start looking at the immune response in GIST. And as you'll hear, this has led to 1 clinical trial, and based on some other work that we're doing right now, we think there'll be a clinical trial number 5 now based out of our work. So very appreciative for the financial support. Thanks. Yes.
When you did the mutational analysis of the adjuvant,
Yeah.
one of the third mutations seemed to have a worse outcome overall. Is that a statistical?
Which mutation?
Was it exon 9?
Yeah, exon 9 has, no, I don't think that's a statistical fluke. I think in the absence of Gleevec, exon 9 is a slightly worse mutation.
It was lower than over time.
If you look far to the right on that curve, then there's very few patients that are still being considered. That follow-up was a median follow-up of 19 months. If you look just in sort of the first 15 months, though, exon 9 definitely does better with imatinib. Now, the problem with these subgroup analyses are the numbers are small. You know, when we design statistics for a clinical trial, it's based on the whole group. And then often we go back and do what we call ad hoc analyses where, well, we can't design an exon 9 trial. We'd never get, hundreds and hundreds of those patients. So it's descriptive data. It's not nearly as compelling as looking at the entire groups. But we don't think, I think that's a fluke of when you look far to the right. We actually have some more updated data now, and we think the answer with exon 9 is probably to stay on the drug for more than 3 years.